Now, children, listen here. Suppose we have to measure the distance towards moon, or the distance from or the distance from Earth to Mars, something like that. Or we have to measure the diameter of, actually angular diameter, okay, and a diameter of Mars or moon, okay, something like that. And all of you know, moon, Mars, or all the celestial objects are very far away from Earth. So there is a method which is used to measure the distance towards moon or towards any planet or to any stars or something like that. And that distance is called parallax method. It's very simple and important. Okay. In the previous exam, they asked like this, name a method used to measure the distance towards moon. Okay, the diameter of moon. Okay, which method is used to measure the distance or the diameter? The method is called parallax method. Parallax method. Okay, parallax method. So what is parallax actually? Actually, it's something, it's a property of eye or something. Suppose I'm looking at this pen. I have a wall on the background of this pen. So I'm looking at the pen through one eye. Like I'm looking at this pen initially. First of all, I'm looking at this pen with my right eye. So the left eye is closed. So I can view the pen. Then when I close my left eye and looking at the pen, it will, you can notice that the position of the pen is just shifted through a small distance. Okay, it's not same actually. So that shift, this is known as parallax. That shift is known as parallax. So what we do in parallax method? In parallax method, suppose S is a star or planet, whatever, is a celestial body at a large distance d. It's a large distance d from Earth. From Earth. So this is a star or planet from a large distance d from Earth, at a large distance d from Earth, and A and B are 2 points on Earth. Suppose A is here and B is somehow somewhere near to A, something as a distance of, suppose A and B are separated by a distance of 1 kilometer. Okay, maybe it's 1 kilometer, 1 meter, whatever. It's up to you. Okay, so A and B are 2 points on Earth separated by a distance B. Separated by a distance B. Okay, so what is S? S is a star or planet, and AB is AB or A and B are 2 points on the surface of Earth separated by a distance B, and D is a distance between Earth and the planet. Clear? Okay. So this will form a triangular, like, I will not say it's a triangle, but a structure like that. I mean a geometrical shape like this. So all of you know that the distance, I mean the D, capital D, is very greater than small letter b, right? Okay, it's very, suppose this is 1 kilometer, this will be maybe light year. It's very greater. Okay, we don't know the distance, but it will be later. So d by b, the ratio will be very less than, sorry. Okay, actually the ratio, the distance is very, okay, the distance is very greater. So since the distance is very greater, see, if the distance is, this distance is very greater than b, okay, I have told you before, the angle, okay, the angle, this is an example of arc. The L is an arc of length L, okay, or this is an arc of length L, and it is subtending an angle theta at the center, and R is the radius. So all of you know what is L or what is theta? Theta equal to L by R. Theta equal to L by R, right? Theta equal to L by R. Okay, so D is very greater than B. Clear? So what will be B by D? Since D is very greater than B, it will be very less than 1, right? That is, since the distance D is very greater than B, this angle is it will be much smaller. It will be very small. It will be very small, and we can treat this like an arc, this AB as an arc of length B. So now we can take AB as an arc of length B. Sorry, yeah, length B. Okay, clear? So this is an arc of length L, and this is the angle, subtended angle theta, center theta. This is the radius R. So if AB can be taken as an arc of length B, or AB is treated as an arc of length B, then we can form an equation here. What is that? So D will be the radius and B will be the arc length. So from that equation we can write theta equal to, both are same, theta equal to arc length, there it is L, right? There it is B. So B by distance D, right? B by D. Clear? B by D. So which implies what will be D? B by theta. B by theta. B by theta. Clear? So I will explain once more. So this is a star. Suppose it is a star or a celestial object or a planet, whatever. And capital D. Okay, this is D. This will be also D. Why? Because the star is it is the fixed actually. Okay, the distance from moon from any point on earth is same. Okay, so this is D and this is also D. Okay, and A and B are 2 points on earth separated by a distance small letter b. A and B are 2 points on earth separated by a distance. This distance is B, small letter b. Okay, small letter b. Now listen, all of you know that the distance towards moon or the planet will be very much greater than distance between the points A and B. It's obvious. Okay, it's sure it will be less. So the capital D, the distance towards the planet will be very much greater than B. So the ratio B by D. So this is the numerator, right? The numerator is much less than the denominator. So the number will be less than 1, very less than 1. So we have already an equation. And we know that for an arc of length L, there will be an angle theta, and the R will be the radius, and theta will be L by R, arc length by radius. That is the angle, arc length by radius. So this angle is very small, and also if B by D is very less than 1, this angle will be very small. Very small. So since this angle is very small, we can treat or we can take AB as an arc of length B, like this arc as an arc of length L. So applying that equation here, which equation? Theta equal to L by R. In this condition, we will get, instead of theta, it is same, theta equal to, instead of the radius R, we have the distance D. So this is the arc D. Okay. So instead of L, we have B. So theta equal to B by D, and the distance D will be B by theta. Distance D will be B by theta. Clear? And this is the method used. This is the parallax method. This method is used to measure the distance. Okay, I think this is clear to you. It's very important. Okay, so this is the method. So this method is called a parallax method. This method is called a parallax method, and it is used to measure the distance towards moon or planets. Okay. It can be also used to measure the angular distance or angular diameter or diameter of the planet. Okay. See, suppose this is a planet. Okay, this is a planet of diameter D. This is a planet of diameter D, and it subtend the diameter subtend an angle at this earth. This is earth. And when we look at the two endpoints of the diameter, okay, we can see an angle. There will be an angle alpha. This is known as angular diameter. Okay, this angle is called the angular diameter of the planet. The question paper, the name will be like that, angular diameter. So the angular diameter of the planet, it will be alpha. Okay, and this is the actual diameter of the planet. This is the actual diameter of the planet, and d is the distance. So applying like this equation, that is theta equal to L by R. Here we have theta equal to L by R. Theta equal to L by R. Okay, theta equal to L by R, and this is alpha. Okay, so theta equal to L by R. So here we have theta, here we have alpha. So alpha equal to, this is the arc length. See, this is the arc length. Always remember the angle, it is always opposite to the arc length. Okay, so this is the arc length d by capital D. Okay, this is the radius. So what will be d? Alpha d. Okay, so here it is theta equal to, we have discussed earlier, theta equal to b by capital D. So what is d? Capital D, b into theta. So like these, from these two equations, we can calculate the distance towards star or planet and the diameter of the planet. So these are all about the parallax method. Okay, and remember one thing, this theta and this alpha, alpha is called angular diameter. Okay, alpha is nothing but angular diameter. And is always measured, theta and alpha are always measured in radian, not in degree. They will all give it the value in radian. So this is the parallax method, very important. Okay, just remember one thing, this method is used to measure the distance, large distance such as towards moon or planet. And what is the method? Okay, and in the previous exam they have not asked questions from this area, but there was one question that is name the distance, name the method to measure the distance. Okay, which is that parallax method. Clear? Parallax method. So this is also about parallax method. Once more, so this is star, this is 2 points A and B. So this will be like arc length. So theta equal to b by d, d equal to b theta. And again, this is a planet. Okay, this is the diameter d, and this is distance alpha. So alpha equal to d by d, d equal to alpha d. Alpha is called angular diameter. That's all. So we have concluded a portion, the first some portions of the units and measurements. Okay, so next we are going to discuss about an entirely different area that's very important for exam. Questions will be sure from that topic. Okay, next topic, it will be very important, dimensions. Okay, dimensions, we will discuss about dimensions later. So it is somehow I will not say it's difficult, but it is a new concept for you. So listen carefully and learn. Okay, next we will discuss about dimensions. So now we have dimensions. Okay, so what do you mean by dimensions? Dimensions are the powers. These are just numbers actually. Okay, so powers to which the base quantities are raised to represent a physical quantity. So the dimension of a physical quantity, is nothing but these are the powers to which the base quantities. What are base quantities? Mass, length, time, temperature. The fundamental quantities are called base quantities. Okay, so base quantity, the powers of base quantity. These are the powers of base quantity. Okay, when you represent a physical quantity, in terms of fundamental quantities, we can represent that. Okay, because all the derived quantities, all the like velocity, volume, mass, whatever may be the quantity. Okay, whatever may be the quantity, all the quantities can be represented. Most of the quantities can be represented in terms of fundamental quantities. Why? That's why they are known as fundamental quantities. Okay, then so almost all quantities can be represented in terms of fundamental quantities. So if you represent a physical quantity in terms of fundamental quantities, then the powers or the exponents of that fundamental quantities are called dimensions. Okay, I will show you an example. See, all of you know that force is a derived quantity because we have learned fundamental quantities. So force is obviously a derived quantity. So what is force actually? Force F equal to ma. That is mass into acceleration, right? Force F equal to ma, mass into acceleration. So what is mass? We don't have any another thing to represent mass. Mass is mass itself. Mass is mass itself, m. What is acceleration? Acceleration is nothing but velocity by time. Acceleration is velocity by time, or it is the rate of change of velocity, or simply we can write acceleration is velocity by time. So acceleration is velocity by time. Okay, then what is velocity? Again, velocity is distance or displacement by time. Velocity is distance or displacement by time. So whatever maybe it is, whether it is distance or displacement, fundamentally it is length actually, right? So velocity is distance by time or displacement by time or simply length by time, right? Or we can call it as displacement by time. Okay, so we have a time already here. So mass into, in terms instead of velocity we can substitute this value f by t into, we have a t already there, so 1 by t. So dividing with t means multiplying with 1 by t, right? Clear? Then what is t into t? It is t square, right? X into x, x square, a into a square. So t into t, t square. So this is m into s by t square. What is s? Distance. Okay. If you are not familiar with s, we can convert into d, distance or displacement. Now listen carefully. Instead of m, I am writing this one, that is m can be represented as capital M in a square bracket. Okay. Distance, that is length, right? So if m is represented as capital M, that is mass is represented as capital M, then length will be represented as capital L. And time will be represented as t. So we have t square. See, so we have represented the derived quantity, that is force, in terms of fundamental quantities such as mass, length and time. Okay, okay. So the derived quantity, that is force, is represented in terms of fundamental quantities such as mass, length and time. Now force equal to, put a square bracket. I will explain why I am writing the square bracket later. So put a square bracket now. So F equal to m, m means m raised to 1, right? Then L means L raised to 1. So this t square will go to the numerator, then it will be t raised to minus 2. See, now the derived quantity force is represented in terms of mass, length and time. Mass, length and time, that is m raised to 1, L raised to 1, t raised to minus 2. M raised to 1, L raised to 1, t raised to minus 2. So this is called dimensions. This is called dimensions. So what are the dimensions of force? So m raised to 1, that is 1, 1 minus 2. So dimensions are the powers. How I told you, dimensions are the powers of base quantities. Okay, so this is m raised to 1, L raised to 1, t raised to minus 2. That is 1, 1 minus 2. 1, 1 minus 2. Clear? Okay. So 1, 1 minus 2. Clear? Then, so the dimension of mass or dimension of in force, the dimension of masses, in force the dimension of mass is 1. In force the dimension of length is 1. What's the dimension of time? It is minus 2. So this is known as dimensions. simply dimensions. Okay, simply dimensions or dimensional formula we will discuss later. Dimensions. Okay, so what is the dimension of force? M raised to 1, L raised to 1, T raised to minus 2. M raised to 1, L raised to 1, T raised to minus 2. So this is called dimension. This is called dimension. So what are dimensions? These are the powers of base quantities when we represent a quantity, a physical quantity in terms of fundamental quantities. Okay, that's called the dimensions. See, now this is an equation, right? This is an equation involving the dimension and the physical quantity. See, this part, the RHS, that is right hand side itself alone called dimensional formula. So the dimensional formula is m raised to 1, L raised to 1, T raised to minus 2. Dimensional formula of force is m raised to 1, L raised to 1, T raised to minus 2. And when we equate the physical quantity with its dimensional formula, we will get dimensional equation. So what is the dimensional equation of force? F equal to, dimension equal to m raised to 1, L raised to 1, T raised to minus 2. So to represent the dimension, okay, we have to know whether it is dimension or not. We use square brackets. So this implies we are writing the dimensional formula of or dimensional equation of force. So this square bracket indicates dimensional equation of force. Okay, so how will you write the dimensional equation of volume? Suppose V is volume, then this represents the dimensional equation of volume. Clear? Suppose we have to represent the dimensional equation of density. Density is represented as rho. Okay, this symbol is new for you. Okay, there are so many symbols like this: rho, theta, eta, or something like that. We will learn that later. Okay, so rho represent density, then a square bracket in and rho. Put a square bracket. The rho inside a square bracket represents the dimensional equation of density. Dimensional equation of density. So what do you mean by dimension? Dimension is nothing but it is a physical. I mean, it's a power. It's a power actually. It's a power which is raised to which the base quantities are raised to represent a quantity. So these are called dimensions. Okay, almost every quantities have dimensions. There are so many quantities which are dimensionless. Okay, and most of the quantities have dimensions. So we will learn. We will discuss about or we will learn the dimensions of some physical quantities later. Next, okay. So what do you mean dimension? These are the powers to which the base quantities are raised to represent a quantity. It is called a dimension. So when you write dimensional formula, put a square bracket. Clear? Okay, that's all about dimension. Next, we are going to discuss about the dimensional equation of certain quantities. Okay. So now we are going to discuss about dimensions of some important physical quantities, both derived and fundamental. Okay, here we have mass. So what is the peculiarity of mass? Actually, mass is a fundamental quantity, fundamental physical quantity. So mass is mass itself, right? So mass has no length, it doesn't depend on length, time, anything. So the dimension of mass is m raised to 1, L raised to 0, T raised to 0. M raised to 1, L raised to 0, T raised to 0. Why L raised to 0 and T raised to 0? Because it doesn't contain any things related to length and time. So L raised to 0 and T raised to 0, that is m raised to 1, put a square bracket, that is m. Dimension of mass is m. M raised to 1 is m, L raised to 0 is T raised to 0 are 1. So 1 into m, which means m. Then again length. Like I told you in the case of mass, it will be length itself L. Then time, it will be m raised to 0, L raised to 0, T raised to 1. So T raised to 1 is T. Again distance and displacement, both are same as that of length. Okay, like distance is measured in meter, displacement is also measured in meter. So they are equivalent. Actually, basically they are length. Okay, they are equal to length. So distance and displacement has the same dimension of length. Okay, then velocity and speed. Okay, doesn't mean the or symbol doesn't mean that they are equal. They are different actually, but velocity and speed have the same dimension. that is displacement by time. Velocity or speed both have the same dimension. Velocity is equal to displacement by time. So what is displacement? Length. So this is L, time is t, that is t means t raised to 1, t means t raised to 1, x is x raised to 1, right. So L by t raised to 1, so t raised to 1 goes to the numerator, that is t raised to minus 1, so L t raised to minus 1. Okay. Again, acceleration. What is acceleration? Acceleration is nothing but velocity by time. Acceleration is velocity by time, another physical quantity, derived quantity, velocity by time. We have velocity, the dimension of velocity is L t raised to minus 1. Okay, like here this is L t raised to minus 1, so that is L t raised to minus 1. So dimension of time is t, right. So this is t raised to 1. Okay, so this t raised to 1 will go to the, okay, this has to be multiplied as t raised to minus 1 with the numerator. With the numerator. So L t raised to minus 1 into t raised to minus 1. Okay, so what is a raised to m into a raised to n? That is a raised to m plus n. That is t raised to minus 1 into t raised to minus 1 is t raised to minus 1 plus minus 1. So what is minus 1 plus minus 1? That is minus 2. So it will be L t raised to minus 2. So once again, mass m, length L, again time t, displacement distance same as that of L, velocity L t raised to minus 1, acceleration L t raised to minus 2.